Okay. Yep. Our next speaker is Adam Cecchetti. He's founding partner and chief executive officer of Deja Security. Previously, he's led teams conducting application and hardware penetration tests for the Fortune 500. Adam is a contributing author to multiple security books, benchmarks, tools, and DARPA research projects. Adam holds a degree in computer science and master's from Carnegie Mellon University in information networking. Adam?
First off, thank you all for joining us here today. I really appreciate you all being part of our first summit. This view here is absolutely fantastic, and it's going to be a bit of the theme of the talk we're going to have about the realities of enterprise blockchain this afternoon, is taking a look to the past and then taking a look to the future. So when I started putting this talk together, I was hoping to talk a little bit about the realities of enterprise blockchain, but as the idea started to form, I realized that really what I'm talking about is the temporality of enterprise blockchain. So I've already been introduced, founder, CEO of Deja Security. A couple of other factoids is I personally led the review and audit on Bitcoin, as well as oversaw the review and audit on Ethereum. Been involved in the crypto space since about 2012, give or take. So let's talk about early ledger technology. Early ledger technology is about 5,000 years old. It was used clay, which was kind of a fork of the dirt project. You can record your transactions in these clay tablets using a stick and cuneiform, and many of the Sumerians did, and civilizations earlier than the Sumerians used these clay tablets to keep track of how goods were moved and transacted from one place to the next. If you wanted to mint or mine one of these tablets, you would throw it in a fire and bake it around 500 or 600 degrees Celsius, and then you would stack them on top of each other and put an entry into a codex. And if you wanted to find the right tablet for the right transaction, you would look at the codex and figure out where and how the one in the stack that you were looking for. Now, this technology had some downsides. If you wanted to erase the record, you simply shattered one of them, or you kind of rubbed over top of it because it was clay. The very low transactional throughput and very high latency. It would take months, if not years, to move one of these tablets from one city to the next. They were difficult but not impossible to forge. You simply had to be literate 4,000 or 5,000 years ago. No small task, but also not impossible. An interesting feature of early ledger technology is that it also was not privacy preserving. Recently, 12,000 of these tablets were unearthed near Iran, and the Assyrian merchants kept very detailed records of where and how and why they were trading. And using a little bit of math, somebody put together this graph of transactions across a set of clay tablets and figured out where some forgotten and lost cities were along trade routes in kind of the Middle East. And some actual archaeological digs have happened as a result. Now, if this sounds familiar, it's because it is very familiar. Blockchain, effectively a transactional ledger of time and events, being recorded in a global state of ordered clay tablets saying, I owe you 2 lambskins of wine, or you owe me 3 sheep and 4 bolts of textile. And the only difference here is that every single time one of these tablets is minted and agreed upon, every single person in the room, every person with a stack of tablets, gets a copy. So everyone gets to maintain every single tablet for every single transaction across all of the trade routes in the Middle East. In reality, how the actual technology works is a list of flat files that are a database that forms a graph of these transactions. And this state gets fairly large because you need to have every record of every transaction for every single thing that's ever happened on any particular blockchain. So at the moment, the Bitcoin blockchain is about 155 gigabytes. Ethereum's coming in about 300 gigabytes. Not exactly something you can run on a cell phone if you want to have full verification of your transactions. So I keep saying verification. So how do we do this? A few of the things have been thrown around today. There's a couple of different ways. If you have proof of work, it's a lot of cryptographic hashing, effectively verifying that the data and the transactions have good cryptographic integrity. Proof of stake is saying, I'm going to lock up a whole bunch of my coins or tokens into this account so that I can vote on which transactions and which snapshot of reality is valid, and then I get some returns and dividends by doing that. So take 1,000 Ethereum, I lock them up in a wallet, I get to say whether or not a transaction is valid, and they pay me very small returns, kind of like mining happens today. And finally, some of the permission blockchain systems use some classic security mechanisms like voting or member gating, and we'll talk a little bit about that in a minute. But effectively what it is one very long store of properties of ordered transactions. A blockchain by default is not privacy enforcing. It is not private. Everyone gets a copy of every transaction. Therefore, you can see every single thing that has ever happened on a blockchain. And it is difficult, but not impossible, to forge a blockchain block. You simply need to have more petahash power or more computing power than half of the network. You need to have more tokens or more coins than anyone else on the network. Or you need to form a cabal with all of your friends and say, we're actually the ones that want to represent what reality is going forward. Or as some people have talked about, access to the private keys for wallets, very simple data management problem. Again, it is about as trivial as being illiterate 4,000 years ago, but it is not impossible to forge a block on a blockchain. So in the theme of something old and something new, some of you may have noticed this strange clay disk as you walked in on the front table. This is the Aetherium blockchain number 4678523 in ancient Sumerian, written on a clay tablet. However, to kind of prove the point of transactional mutability, my alphabet was wrong, and so I had to erase it and start over. So the one in the back is written in actual later cuneiform, and it effectively says Deja Cecchetti. So close enough to Deja vu security in ancient Sumerian if you're into those kinds of things. So let's take another look backwards as we're sort of looking here. Early computing, mainframes. Some of the first multi-user systems, they had a flat memory space. The compute and storage on them was incredibly expensive and very time-consuming. A lot of the research around early mainframes was on getting data transactions as well as throughput to become faster. And there was very little code or data protection. There was no privacy. There was no ability to gate who or didn't have access to various parts of the memory if you were running on these things. Effectively accessible to anyone that had a connection directly to the mainframe. So Aetherium is a new computer, a Turing-complete machine. It has a flat memory address space. It is a globally distributed system of which anyone has access to via a peer-to-peer network. It tracks the program and application state on a blockchain, so every single time a transaction happens or every single time something in a program happens, it updates that state into the blockchain. And the term smart contracts is simply an application that runs on top of the Aetherium platform that gates changes and that eventually get written to the EVM. Now it has this very interesting property, is it's not privacy preserving. By default, every user can see every transaction or every execution that every program on this global computer performed. Let's take a look backwards again at some early storage technology, ROM. Most people in the room are familiar with ROM, but effectively what it was a collection of data or code burned into a chip once via diode matrix. Diode matrix is simply a fuse. You blow the fuse, you get a 1 or a 0, and then you can read out with that data or code from a ROM chip. So you could write this once to a ROM chip and read it back multiple times. The data or code was accessible by anyone that knew where the chip was or knew how to talk to the chip. And you would destroy these chips by blanking them with a command, flashing them with UV, or literally taking a hammer to them. In the case of a diode matrix, that was the only way to destroy them. A smart contract is effectively a collection of data and code stored into a particular address in the Aetherium computer. It is writable exactly once, which means you can't update it, you can't patch it, and you call a special operation to be able to destroy it. So there's a special opcode in the computer itself called suicide. Smart contracts have this interesting property of not being patchable, and because the Aetherium computer is so new, we haven't quite worked out what all the side effects in the computer are. Additionally, there's a lack of well understood and audited examples, so to get this right can be a very difficult and challenging problem. Some of the things we've been looking at from both a research and a active engagement perspective at Deja Vu Security is how to get smart contract auditing right. I started putting together a list of these things. I'm not going to go through this. Happy to share this later. But this is the bug classes, not the types of bugs that can potentially happen in the type of application that you run on top of this distributed world computer. Now, as I had mentioned, most of the focus right now for Aetherium isn't on security and privacy. It's on how do we get higher transactional throughput with this computer, with this one global mainframe. How do we get more things through it so we can get our crypto kitties and bet on our esports and do whatever it is that we may want to do. The current plan by Aetherium is to split the network into multiple pieces, and then different applications will run in different places. And if that sounds like we're going to split the computer into multiple computers, it's because it's pretty close. The way that this will be performed is with a hybrid proof of stake, proof of work model, which will verify the transactions, the goal of which is to be as performant as the Visa network, which is approximately 1,600 transactions per second. And depending on whose statistics you believe, the current transactions on the Ethereum network is around 7 to 20 per second. So there's a lot of ground to go. There's a lot of reason they're focusing on this, because the more transactions per second you get, the more adoption of this one global computer that will occur. The more users, the more applications will jump onto the platform. So let's go back and kind of do a quick summary to make sure we're still all on the same page. Ethereum and many of the other application-based blockchain systems are effectively a globally accessible computer of very carefully managed applications that have apps stored in a ROM-like manner, or a write-only once. These programs gate logical access to the blockchain, which keeps store of the state and the transactions. So you have a computer, you have applications, all of the data and state is stored on the blockchain itself. All right, let's see. As I had mentioned, most of the research and most of the development right now is focused on transactionally and input, but much like the early days of any computer, we're seeing the exact same problems start to arise. Patching is clearly an issue. We have two options for patching in Ethereum. One is a hard fork, and the other is nothing else. Data privacy, there is no focus on data privacy at the moment, other than some very simple upgrades to the Ethereum VM. Hopefully that'll happen more in the future. User privileges, process separation, code isolation. Pretty much every single fundamental problem with security that you have when you build a new computer is currently happening inside of the Ethereum ecosystem. Why does this sound familiar? Well, it sounds familiar because we've seen this before. We're having a massive sense of deja vu. We had these problems with mainframes, we had these problems with PCs, we had this problem with mobile, we had this problem with the web. So an interesting concept that I was thinking about is that computers are fantastic at looping humans. And if you don't believe me, hit print, wait for it to fail, go to the printer, walk back to your computer, try and hit print, walk back to the printer, and you will do this 30 or 40 times until your print job kind of done. So the computer's loop put you into a loop versus you looping the computer. But every time we build one of these new computers, every time we move the Turing machine or the computer itself from mainframe to PC to mobile to whether it's a smart contract system, it doesn't matter, we end up having the exact same 10 problems. Determinism, reliability, availability, communication, security, distribution, fault tolerance, scalability, isolation, and identity. Now, we've made some good progress depending on if you're in the mainframe, PC, mobile, or cloud space, but we're still solving some of these problems in the Ethereum as well as the smart contract ecosystems. Now, let's take a look at how cross-organization syncing is still done. If you're part of any large organization and you're sharing information from one org to the next, you're probably doing it in one of three ways. You're either shipping hard drives and tapes, somebody is unloading them from a station wagon, plugging them into your organization, you're SFTPing flat files from one org to the other, or you're using some type of batch mechanism over some REST API to send data back and forth from one org to some other place. Manual conflicts and resolution is still done over the phone. So two people will get the updates, try and merge them, and then call each other, which can be a very long and tedious process and can take weeks to resolve. So some of the killer use cases of enterprise blockchain systems is sitting right there in a cross-organization or cross-team mechanism, where you have 5 large financial institutions that all want to interact, but no one wants centralized ownage of the technology, where you have multiple teams in an organization that need to have distributed transactions that talk to each other or update each other, but no one is the single point of authority for any of those. And why is that? The enterprise versions of smart contract systems and blockchain systems give you 3 very interesting properties. One is they're instantly audible. You don't have to get on the phone and do manual reconciliation of transactions. You don't have to look and see who, how, and when did where or where did what. They are permissioned. You can gate the members that come in and out of these systems by effectively saying, I only want these 3 organizations, or I only want these 2 teams to be able to participate in this enterprise system. And if they're properly utilized, they can actually have privacy in transactions. So there's two very large organizations working on this problem right now. One is Quorum. It's a project sponsored by JPM Morgan Chase, led by Ambo Bardet. It's an Aetherium fork that is an enterprise version of the Aetherium ecosystem that enables you to have a permissioned private blockchain by replacing the proof of work with a different consensus mechanism. The peer-to-peer network permissions nodes to be able to jump on and off as necessary, and enables organizations to do cross-syncing as well as transactional operations in a very succinct and performant manner. How does it do this? Well, using some of the classic things that we've used in security are tried and true. It uses a whitelist of nodes. It says you can be on our network or you can't be on our network. Very simple. Transactions are private by using things like public key cryptography, as well as enabling that data to only be seen by certain individuals by using side chains and private chains. So we don't all have the exact same set of clay tablets. We're all using different sets depending on how and where and why that particular chain is implemented. Another system is called Hyperledger Fabric. It's an IBM-sponsored project that was donated to the open source community. It's very functionally similar to Quorum. It has a membership service that gates access in and out of it, so only the organizations or individuals that we want to have talk to that particular blockchain are the ones that we allow on. The ordinal service orders the blocks. So instead of having a distributed set of people decide what the future is, you have one central authority that says, send us your blocks, we'll put them in the correct order that we need to be able to have transactional integrity across all of these systems. And they simply call smart contracts chain code in this particular system. So Quorum and Hyperledger, they're very focused on scalability as well as enabling these systems to scale out to different organizations. New blocks are minted every 50 milliseconds versus every 7 seconds on the Ethereum network or every 10 minutes on the Bitcoin network. So if you have a performant use case, you can either use these projects for that or fork these projects for that to sync between different organizations. They have private transactions as well as they have private blockchains. So where to from here? So what I find interesting, the most interesting about all of these problems is that we really haven't changed anything in 5,000 years. We have taken sticks and marked in clay and said this will be the transaction and this will be the record for that transaction. We've moved it to paper and then silicon and then to literally into ether. So some of the most interesting problems in this space to me are how do we bridge from the real world and the social gap into using these technologies. And so those are some of the questions I hope to speak with you about later this afternoon. I hope this has been informative to you all, and thank you very much for taking the time to be here today.
Any questions for Adam? Please do grab Adam. If we got one question, and then we'll
one question I had was, I saw a bit on one of the slides, and I was curious if you foresee any enterprise applications of this technology, and specifically zero-knowledge proofs, and if there's any mechanisms by that might be a sort of newer cryptographic innovation that we can think about ways to integrate that into various blockchain solutions.
Absolutely. So the question was, do you foresee how to integrate zero-knowledge proofs into enterprise applications? So very briefly, a zero-knowledge proof is something that enables someone to prove that they know that someone else has done something or knows something without actually knowing what it was. So you have the ability to know that someone has a piece of information without either them revealing it or you revealing the specifics of that information. So that's very useful in having two people basically say, did you do something or did you perform something without ever having to reveal what exactly it is that you did. And so yes, I do see a lot of good application for those in two organizations. So you have two enterprises or two banks or two facilities that want to say, hey, prove to me that you did this thing, but don't prove to me what your customer name was. Or prove to me that you actually gave this much money to someone, but don't reveal any of that information about exactly what happened in the background to make that happen. So I absolutely do see a good use case for that. The common referral name to this technology in the space is called Z-Snarks or Z-Starks, but they're not quite ready yet. So on the Aetherium network, if you have a Z-Snark or you have a Z-Stark, it requires a ridiculous amount of computing power and a ridiculous amount of time to use. And the way the computer is constructed, similar to a mainframe, both compute and storage are very expensive. So until there's a fundamental change in the Aetherium computer itself, I don't see that happening. But other organizations like Quorum and other some of the enterprise versions have started to address that, saying, hey, this is a use case. We do want to be able to prove something to someone else without revealing exactly what we did. So I see that being adopted faster in the enterprise than in the public sector. It's a great question. Thank you. Any other questions?
Okay, thanks again, Adam.